The universe is vast, it stretches beyond our comprehension, filled with stars, galaxies, and nebulae. But what if I told you that the universe is mostly empty space? This emptiness, far from being insignificant, holds the key to understanding the universe's structure and evolution. We often picture the universe as a dazzling tapestry of celestial objects. We envision swirling galaxies, radiant nebulae, and the twinkling of distant stars. Yet, this vision, while captivating, obscures a fundamental truth. The universe is dominated by voids. These are vast, desolate regions where matter is scarce, and darkness reigns. These voids are not merely empty spaces, they are dynamic entities shaped by the interplay of gravity, dark matter, and the expansion of the universe itself. They are cosmic laboratories where we can study the fundamental forces that govern our existence. The existence of these voids challenges our perception of the universe. It compels us to look beyond the familiar light and confront the profound implications of a cosmos defined by its emptiness. Imagine a canvas of unimaginable size. On this canvas, galaxies are scattered like brushstrokes, forming intricate patterns and vast, interconnected structures. This is the cosmic web, a tapestry of matter and energy that spans the observable universe. The cosmic web is not a random scattering of galaxies, it is a testament to the power of gravity, which drew matter together over billions of years, forming filaments, walls, and clusters of galaxies. These structures, illuminated by the light of billions of stars, trace the paths along which the universe evolved. But between these luminous strands lie the voids, vast, dark expanses that dwarf the galaxies themselves. These voids are not empty in the truest sense. They contain a sparse scattering of galaxies, a thin haze of gas, and the elusive presence of dark matter. Yet compared to the bustling hubs of galactic clusters, voids are realms of profound emptiness. They are the silent spaces between the notes, shaping the cosmic symphony by their very absence. For centuries, humanity placed itself at the center of creation. We gazed upon the night sky, awestruck by the celestial dance, and assumed a privileged position in the cosmic order. But as our understanding of the universe grew, so too did our realization of its indifference to our presence. We now know that Earth is but one planet orbiting an average star in a galaxy that houses billions of its kind, and our galaxy, the Milky Way, is just one of trillions within the observable universe. This humbling realization extends to our cosmic address. Astronomical observations suggest that the Milky Way itself resides within a void, a region of space with a lower density of galaxies than the cosmic average. This void, known as the KBC void or the local hole, spans hundreds of millions of light-years. Its existence challenges our assumptions about the universe's uniformity and raises intriguing questions about our place within it. The realization that we reside within a cosmic void underscores the vastness of the universe and the relative insignificance of our own galactic neighborhood. It forces us to confront the possibility that the universe's grand design might be shaped not only by the presence of matter, but also by its absence. The universe is a symphony of forces, a delicate balance between creation and destruction, expansion and contraction. The voids, far from being passive bystanders, play a crucial role in this cosmic orchestra. They are the silent partners in a dance that has spanned billions of years, their emptiness shaping the distribution of matter and the evolution of galaxies. The voids, born from the tiniest fluctuations in the early universe, expanded over eons, driven by a force we still barely understand, dark energy. This mysterious entity, thought to permeate all of space, acts as an anti-gravity, pushing galaxies apart and stretching the very fabric of space-time. Within the voids, where matter's gravitational pull is weakest, dark energy exerts its influence most profoundly. Here, it stretches space at an accelerating rate, driving the expansion of the voids and shaping the large-scale structure of the universe. The voids are not merely empty spaces, they are the silent conductors of the cosmic orchestra, their influence shaping the music of the spheres. They are a testament to the universe's capacity for both grandeur and subtlety, a reminder that even in nothingness there is profound beauty and mystery to be found. Imagine a tapestry woven not of thread but of galaxies, billions of them, each a swirling island of stars, gas and dust. Our Milky Way is but one thread in this cosmic tapestry, a web of interconnected structures, a balance between abundance and emptiness. At grand scales, the universe resembles a three-dimensional spiderweb, its threads spun from galaxies, stretching across billions of light-years. This cosmic web is a testament to gravity's pull, drawing matter into vast, interconnected filaments and walls. These luminous strands trace the universe's evolution, marking boundaries between light and darkness. Between these filaments lie vast, desolate cosmic voids. These voids, spanning millions of light-years, are regions of profound emptiness, where galaxies are scarce and darkness reigns. They shape the universe's structure by their absence. The existence of these voids, juxtaposed against the cosmic web, challenges our understanding of the universe. The cosmos is defined by both presence and absence, by the vast, silent spaces between the stars. The cosmic voids, far from being inert spaces, are dynamic entities, shaped by gravity, dark matter, and the universe's expansion. They influence the distribution of matter and the evolution of galaxies over billions of years. Imagine a vast cosmic ocean, its surface rippling with gentle waves. These waves represent subtle variations in density, remnants of the universe's tumultuous birth. Gravity amplified these variations, forming galaxies and clusters. The troughs deepened, becoming the voids that punctuate the cosmic landscape. The voids are not merely passive recipients of this cosmic flow, their gravitational pull drew material away, deepening their emptiness. This process, known as gravitational evacuation, amplified the contrast. The voids influenced the evolution of galaxies. Galaxies' paths were shaped by the gravitational tug of surrounding matter. This interplay influenced galaxy collisions and star formation. The cosmic voids played a subtle yet profound role in sculpting the universe. They were active participants in the cosmic dance woven into space-time. To understand cosmic voids, we must journey back to the universe's infancy, to a fraction of a second after the Big Bang. The universe was an inferno of energy, a seething cauldron of particles and radiation. Quantum fluctuations created tiny density variations, tipping the scales in favor of gravity, setting in motion the formation of galaxies and voids. These voids are echoes of the Big Bang, remnants of the universe's earliest moments. The vastness of cosmic voids evolves over billions of years, adding complexity to the cosmic tapestry. Gravity draws matter together, but dark energy, a cosmic anti-gravity, shapes the universe's destiny. Dark energy permeates space, driving the accelerated expansion of the universe. In dense galaxy clusters, gravity binds structures together. In cosmic voids, dark energy reigns supreme. As the universe expands, voids stretch wider. This expansion counteracts gravity, shaping the universe's structure. Dark energy accelerates space expansion, pushing galaxies apart. Cosmic repulsion isolates galaxies, suggesting a future dominated by voids. Voids are dynamic, shaped by gravity, dark matter, and dark energy. They offer clues to dark energy and the cosmos's fate. Our Milky Way galaxy, nestled within the local group, resides in the KBC void, a stark reminder of the universe's penchant for emptiness. It dismantles the notion of a uniformly populated cosmos, replacing it with vast structures and immense voids. Our presence within a void offers a unique perspective. It is a universe that constantly challenges our perceptions. Within the vast cosmic tapestry, where galaxies cluster in luminous strands and filaments, the Boötes Void stands apart, a region of astonishing emptiness that stretches across 330 million light-years, dwarfing all other known voids in scale. Discovered in 1981 by astronomer Robert Kirshner and his team, this cosmic abyss, located some 700 million light-years from Earth in the constellation of Boötes, challenges our understanding of the universe's structure and the forces that govern it. Imagine a sphere so vast that if our Milky Way galaxy were a grain of sand, the Boötes Void would be the size of the Earth. Within this immense volume, one might expect to find thousands upon thousands of galaxies, swirling islands of light and matter, each home to billions of stars. Yet, observations reveal a starkly different reality. Only a few dozen galaxies, a paltry 60 or so, have been detected within the Boötes Void, clustered in a peculiar tube-like structure that pierces its heart. This profound emptiness, a cosmic desert in a universe teeming with galaxies, poses a fundamental question: why is the Boötes Void so empty? What forces conspired to create this immense region where matter seems to have been banished, leaving behind a cosmic echo chamber where the whispers of the early universe may still resonate? The Boötes Void is not merely an anomaly, it's a cosmic enigma, a challenge to our understanding of how the universe evolved from a nearly uniform sea of energy into the intricate tapestry of galaxies, clusters, and voids we observe today. It beckons us to explore the interplay of gravity, dark matter, and dark energy, those unseen sculptors of the cosmos, and to unravel the mysteries that lie hidden within its depths. Within the vast cosmic tapestry where galaxies cluster in luminous strands and filaments, the Boötes Void stands apart, a region of astonishing emptiness that stretches across 330 million light-years, dwarfing all other known voids in scale. Discovered in 1981 by astronomer Robert Kirshner and his team, this cosmic abyss, located some 700 million light-years from Earth in the constellation of Boötes, challenges our understanding of the universe's structure and the forces that govern it. The Boötes Void's stark emptiness contrasts with the surrounding cosmic landscape. It's encircled by massive structures like the Great Wall, the Coma supercluster, and the Hercules supercluster. These structures highlight the Boötes Void's anomalous nature. It's as if the universe carved out this immense void. Astronomers propose it formed from low-density fluctuations or merging smaller voids. The Boötes Void's scale and shape suggest other, less understood forces at play. The Boötes Void is a dynamic environment shaped by gravity, dark matter, and dark energy. These forces shape the cosmos, driving galaxy evolution. Gravity forms stars, galaxies, and clusters. In cosmic voids, gravity's grip weakens. Dark matter forms a scaffolding, holding galaxies together. In the Boötes Void, dark matter distribution holds clues. Less dark matter means weaker gravity, hampering galaxy formation. Dark energy drives cosmic expansion. It pushes galaxies apart, stretching spacetime. This cosmic repulsion shapes the Boötes Void. As the universe expands, so does the void. This expansion counteracts gravity, shaping the universe. The Boötes Void, with its sparse population of galaxies and vast stretches of emptiness, offers a unique window into the early universe, a cosmic time capsule preserving the conditions that prevailed billions of years ago. Unlike galaxies where stars are born and die, enriching the interstellar medium with heavy elements or galaxy clusters, where collisions and mergers reshape galaxies over time, voids remain relatively pristine, their contents largely unchanged since the universe's infancy. This pristine environment makes the Boötes Void an ideal laboratory for studying the fundamental properties of the universe. By observing the few galaxies that do reside within the void, astronomers can glean insights into the processes of galaxy formation and evolution in the absence of significant gravitational interactions with neighboring galaxies. Furthermore, the void's vast emptiness provides a unique opportunity to study the cosmic microwave background radiation, the faint afterglow of the Big Bang, with minimal interference from intervening matter. This radiation, a fossil from the universe's earliest moments, carries information about the universe's age, composition, and evolution. By studying the cosmic microwave background radiation within the Boötes Void, astronomers can probe the conditions that prevailed in the early universe, testing cosmological models and refining our understanding of the universe's origins. The Boötes Void, therefore, is not merely a region of emptiness, it's a cosmic treasure trove, holding clues to the universe's deepest secrets. It's a reminder that even in the absence of light and matter there is much to be learned, much to be discovered about the nature of the cosmos and our place within it. The Boötes Void, with its sparse population of galaxies, offers a unique window into the early universe, a cosmic time capsule preserving conditions from billions of years ago. This pristine environment makes the Boötes Void an ideal laboratory for studying the universe. It's a cosmic treasure trove, holding clues to the universe's deepest secrets. The Boötes Void, with its stark emptiness, contrasts with bustling galaxy clusters. It challenges our perceptions, reminding us the cosmos is a tapestry of matter and absence. Voids shape the universe's structure, influencing galaxy formation. They are silent partners in a cosmic dance spanning billions of years. Even in emptiness, profound mysteries await. Cosmic voids, vast expanses of emptiness, were sown in the universe's infancy, mere fractions of a second after the Big Bang. The universe was a turbulent ocean, roiled by quantum fluctuations, tiny variations in energy density. Imagine a vast, dark ocean, its surface constantly shifting, rippling with waves. These fluctuations represented regions where energy density was slightly higher or lower. These fluctuations set in motion events shaping the universe's matter distribution. Regions with increased energy density had a stronger gravitational pull. These denser regions drew in more matter, amplifying density contrast. Over eons, these regions became the seeds of galaxies and clusters. Regions with lower energy densities experienced weaker gravitational pull. These regions expanded outward, their matter density thinning. The seeds of abundance and emptiness were sown in the universe's first moments. As the universe expanded and cooled after the Big Bang, gravity shaped the cosmic web, drawing matter into stars and galaxies, and creating vast cosmic voids. Gravity, the universe's sculptor and excavator. The formation and evolution of cosmic voids were not solely governed by ordinary matter. Dark matter played a crucial role in shaping the universe's large-scale structure. Unlike ordinary matter, dark matter does not interact with light. Its presence is inferred through gravitational effects on visible matter. Dark matter forms a vast, invisible halo around galaxies and permeates the cosmic web. As gravity diligently sculpted the universe's large-scale structure, another force, a cosmic anti-gravity known as dark energy, was subtly at play, shaping the universe's destiny on grand scales. This enigmatic force, thought to permeate all of space, acts as a counterpoint to gravity's pull, driving the accelerated expansion of the universe. In the dense regions of galaxy clusters, gravity's influence still holds sway, binding these structures together against the cosmic flow. However, within the vast expanses of cosmic voids where matter is scarce, dark energy's influence reigns supreme. As the universe expands, the voids expand along with it, their emptiness stretching ever wider. This expansion is not merely a passive stretching, it is an active force, counteracting gravity's pull and shaping the large-scale structure of the universe. Within the voids where gravity's grip is weakest, dark energy accelerates the expansion of space, pushing galaxies away from each other and driving the voids to grow ever larger. This cosmic repulsion, subtle yet relentless, has profound implications for the universe's fate, suggesting a future where voids dominate and galaxies become increasingly isolated, islands in a vast, ever-expanding sea of darkness. Cosmic voids, far from desolate, are invaluable laboratories. They offer insights into the early universe, dark matter, and dark energy. Studying the cosmic microwave background reveals the universe's age, composition, and evolution. Voids also help map dark matter and study dark energy's influence on cosmic scales. Galaxies in voids offer clues about galaxy formation in low-density environments. As the universe continues its relentless expansion, driven by the enigmatic force of dark energy, cosmic voids will dominate the cosmic landscape. The cosmic web will stretch, isolating galaxy clusters and driving galaxies further apart. Voids will expand and merge, becoming vaster and emptier, Galaxies will drift apart, becoming isolated islands in a sea of darkness. The future of the universe is a future dominated by voids. The discovery of vast cosmic voids like the Boötes Void presents a profound paradox. How can a universe governed by gravity manifest such extreme density variations? The universe revels in contrasts. It is a realm where the small and vast coexist. This duality is a testament to the universe's complexity. The Boötes Void challenges the cosmological principle, which asserts the universe is homogeneous and isotropic. This principle suggests no preferred locations or directions in the universe, yet vast voids like Boötes seem to contradict this. Are these voids statistical anomalies or signs of a needed revision? Section 3. The limits of uniformity. The challenge posed by cosmic voids to the cosmological principle highlights a fundamental aspect of scientific inquiry: the constant need to refine our understanding in the face of new observations and discoveries. The cosmological principle, though a powerful tool for understanding the universe, is ultimately based on observations and assumptions that are subject to revision as our knowledge expands. The concept of homogeneity, as applied to the universe, is not absolute but rather scale-dependent. On smaller scales, such as those of galaxies and galaxy clusters, the universe is clearly inhomogeneous. Stars cluster into galaxies, galaxies clump together into clusters, and clusters group into superclusters, forming the intricate web-like structure we observe. However, as we zoom out to larger and larger scales encompassing billions of light-years, the universe appears to become smoother, with the variations in density averaging out. The cosmic microwave background radiation, for example, exhibits remarkable uniformity in all directions, suggesting that the early universe, at least on very large scales, was remarkably homogeneous. The discovery of cosmic voids, however, suggests that this averaging process may not be perfect, and that significant inhomogeneities can persist even on the largest scales we can observe. The Boötes Void, for instance, spans a significant fraction of the observable universe, challenging the notion of a completely homogeneous cosmos. Section 4. Embracing the paradox. The tension between cosmic voids and the cosmological principle deepens our understanding of the universe. It compels us to refine our models and explore new research avenues. Science progresses through resolving paradoxes and reconciling contradictions. Cosmic voids challenge us to embark on a journey of discovery. They may represent a breakdown of the cosmological principle on large scales. Perhaps the universe exhibits large-scale density variations. Our understanding of the cosmological principle may need refinement. Homogeneity might imply statistical uniformity, allowing rare fluctuations. Cosmic voids compel us to re-evaluate our assumptions. The cosmos is vast, complex, and full of mysteries. Section 5. Voids, beacons in the cosmic sea. Cosmic voids, once thought insignificant, are now seen as integral to the universe's structure and evolution. They offer insights into dark matter, dark energy, and the universe's expansion. Studying voids helps us understand the universe's early history and the formation of stars and galaxies. Voids illuminate the universe's deepest secrets, guiding us toward a more complete understanding of the cosmos. The Boötes Void, in its vastness and emptiness, invites speculation. Could this cosmic desert harbor the remnants of advanced civilizations? Imagine a civilization capable of harnessing the energy of entire stars. Such a civilization might have left subtle traces within the Boötes Void. Perhaps the void's sparse galaxies are the remains of a once thriving galactic neighborhood. The Boötes Void, in its silence and emptiness, might hold more than just the echoes of vanished civilizations. It could harbor messages, subtle patterns imprinted on the fabric of space-time, waiting to be deciphered by those who know how to listen. Imagine a civilization seeking to communicate across the vast gulfs of interstellar space, not with radio waves or laser pulses, but with the very structure of the universe itself. Such a civilization might have chosen the Boötes Void, a region of relative calm and stability, as a cosmic canvas upon which to inscribe their messages. These messages might take the form of subtle variations in the density of dark matter, patterns etched into the cosmic microwave background radiation, or even slight anomalies in the expansion rate of the void itself. Deciphering such messages would require not only advanced technology, but also a fundamental shift in our understanding of the universe and the possibilities of communication. The very emptiness of the Boötes Void could itself be a message, a deliberate act of cosmic art designed to attract attention and spark curiosity. Perhaps the void is a beacon, a cosmic signpost left by a long-gone civilization, inviting others to unravel its mysteries and uncover the knowledge it holds. The Boötes Void, with its vast scale and low matter density, presents a unique environment for cosmic engineering projects of unimaginable scope. Could this seemingly empty region of space be a testing ground for advanced technologies, a cosmic laboratory where civilizations far more advanced than our own experiment with the fundamental laws of physics? Imagine a civilization capable of manipulating dark matter and dark energy, the invisible forces that shape the universe's destiny. The Boötes Void might be a playground for advanced civilizations, pushing the limits of technology and cosmic engineering. Beyond the Fermi paradox, the void's silence. The Boötes Void's profound emptiness raises intriguing questions about the Fermi paradox, the apparent contradiction between the high probability of extraterrestrial life and the lack of observational evidence for it. If the universe is teeming with life, as some theories suggest, then why haven't we encountered any signs of it, particularly in a region as vast and seemingly untouched as the Boötes Void? One possibility is that advanced civilizations, rather than broadcasting their presence, choose to remain silent, concealing themselves from potential threats or simply observing the universe without interfering. The Boötes Void, with its isolation and lack of readily observable resources, might be an ideal location for such a civilization to remain hidden, observing the universe from the shadows. Another possibility is that advanced civilizations are transient, their lifespans limited by resource depletion, internal conflicts, or technological singularity events that propel them beyond our comprehension. The Boötes Void, in its vastness and age, might have hosted numerous civilizations throughout its history, their rise and fall leaving behind only faint traces, if any. The void's silence, therefore, might not be an indication of the absence of life but rather a consequence of the vastness of time and space, the fleeting nature of civilizations, and the possibility that advanced intelligence chooses to remain hidden from view. The Boötes Void, in its enigmatic emptiness, serves as a powerful reminder of the universe's vastness, its mysteries, and the limitations of our current understanding. It challenges us to confront the unknown, to embrace speculation and imagination, and to acknowledge that our current scientific framework, though impressive, is likely just a glimpse into a far grander and more complex reality. The void's emptiness, far from being a sterile wasteland, is pregnant with possibilities. It invites us to explore the boundaries of our imagination, to consider the existence of advanced civilizations, cosmic engineering projects, and perhaps even realities beyond our current comprehension. The Boötes Void, in its silence, speaks volumes. It whispers of the universe's boundless capacity for both creation and negation, for both abundance and emptiness. It reminds us that the cosmos is not a static, unchanging backdrop, but rather a dynamic, evolving entity, full of surprises and wonders waiting to be discovered. As we continue to explore the universe, peering deeper into the cosmos with ever more powerful telescopes and instruments, we can expect to uncover more mysteries, more anomalies that challenge our current understanding. The Boötes Void, in its enigmatic silence, stands as a beacon, a reminder that the universe is a vast, complex, and ultimately unknowable entity, forever unfolding its mysteries before us. The Boötes Void, a cosmic abyss stretching across hundreds of millions of light-years, stands as a testament to the universe's capacity for both grandeur and enigma. Its profound emptiness, far from being a sterile wasteland, has captivated astronomers and laypeople alike, sparking curiosity and igniting the flames of speculation. We are drawn to the void's mystery, to the possibility that it holds secrets beyond our current comprehension. Could this vast expanse of emptiness harbor the remnants of advanced civilizations, the echoes of cosmic engineering projects, or perhaps even glimpses into dimensions beyond our own? The void's allure lies not only in its potential to upend our understanding of the universe but also in its stark beauty. In a cosmos filled with the dazzling light of trillions of stars, the void's darkness offers a different kind of splendor, a reminder that absence can be as powerful as presence, silence as profound as sound. The Boötes Void beckons us to contemplate the universe's extremes, to journey beyond the familiar comfort of stars and galaxies, and confront the awe-inspiring scale of cosmic emptiness. It is a journey that challenges our perceptions, stretches the limits of our imagination, and ultimately deepens our appreciation for the cosmos and our place within it. The discovery of cosmic voids, particularly structures as immense as the Boötes Void, has profoundly altered our understanding of the universe. It has challenged our assumptions about the cosmos's uniformity, the distribution of matter, and the role of gravity in shaping the large-scale structure we observe. We once envisioned a universe relatively evenly populated with galaxies, a cosmic sea of stars stretching infinitely in all directions. However, the existence of voids has shattered this paradigm, revealing a cosmos far more complex and intricate than we could have imagined. The universe, we now know, is not a smooth, homogeneous expanse, but rather a tapestry woven from both matter and its absence, a delicate balance between the luminous threads of galaxies, clusters, and filaments, and the vast, dark voids that lie between. This realization has forced us to re-evaluate the role of gravity in shaping the cosmos. Gravity, once thought to be solely responsible for drawing matter together, is now understood to play a more nuanced role, both assembling matter into luminous structures and simultaneously carving out vast expanses of emptiness. The discovery of voids has ushered in a new era of cosmological research, one that embraces the universe's complexity and seeks to understand the interplay of gravity, dark matter, dark energy, and the expansion of the universe itself in shaping the cosmos we observe. The exploration of cosmic voids is akin to setting sail into uncharted waters, leaving behind the familiar shores of galaxies and clusters to venture into a realm where emptiness reigns supreme. It is a journey into the universe's unknown, a quest to unravel the mysteries that lie hidden in the darkness. Just as early explorers set sail across vast oceans, driven by curiosity and a thirst for discovery, astronomers are now peering into the depths of cosmic voids, using ever more powerful telescopes and instruments to chart their contours, analyze their contents, and unravel their secrets. These explorations have already yielded remarkable insights. By studying the few galaxies that do reside within voids, astronomers are gaining a better understanding of galaxy formation and evolution in low-density environments, where gravitational interactions with neighboring galaxies are minimal. The study of voids has also provided crucial insights into the nature of dark matter and dark energy, the invisible forces that shape the universe's destiny. By analyzing the motion of galaxies within and around voids, astronomers can map the gravitational influence of dark matter, while the expansion rate of voids themselves offers a sensitive probe of dark energy's enigmatic properties. The exploration of cosmic voids is still in its infancy, but it has already revolutionized our understanding of the universe. As we continue to push the boundaries of observation and theory, we can expect even more remarkable discoveries from these seemingly empty regions of space. The study of cosmic voids is a profound quest to understand our place in the universe. By exploring the universe's extremes, we gain a deeper appreciation for its intricate workings. The quest for cosmic understanding is a journey without end, a continuous process of exploration and discovery. Cosmic voids remind us that the universe is far grander and more wondrous than we can imagine. The existence of cosmic voids, far from diminishing our place in the universe, underscores the remarkable interconnectedness of all things. We are not isolated observers, looking out upon a vast and indifferent cosmos, but rather active participants in a cosmic dance that has spanned billions of years. The atoms that make up our bodies, the air we breathe, the very earth beneath our feet, all were forged in the hearts of stars that lived and died long ago, their remnants scattered across the cosmos by supernova explosions, eventually coalescing into new stars, planets, and ultimately, life itself. The cosmic web, with its filaments, walls, and voids, is a testament to this interconnectedness, a visible reminder that the universe is not a collection of isolated objects but rather a dynamic, evolving system, where every part is linked to every other. Our presence within the KBC void, a region of relative emptiness within the cosmic web, is a reminder that even in the universe's quietest corners, the echoes of creation resonate. We are a product of the universe's grand evolution, a testament to its capacity for both complexity and beauty. The Boötes Void, in its vastness and emptiness, serves as a powerful symbol of the universe's boundless capacity for wonder and possibility. It is a blank canvas upon which we can project our hopes, our fears, and our wildest imaginations. The void's emptiness, far from being a source of despair, can be seen as an invitation to explore, to dream, and to imagine possibilities beyond the confines of our current understanding. It reminds us that the universe is far grander, more mysterious, and more awe-inspiring than we can possibly comprehend. Could the void harbor life as we've never known it, existing in forms and dimensions beyond our current imagination? Could it be a realm where the laws of physics as we understand them break down, giving rise to phenomena that challenge our very notions of reality? The possibilities are as limitless as the void itself. The Boötes Void, in its silence, speaks volumes. It whispers of the universe's infinite potential, its capacity for both the familiar and the unknown, the mundane and the extraordinary. It is a reminder that the cosmos is a realm of endless wonder, a place where discovery never ceases and where the boundaries of human understanding are constantly being pushed. The Boötes Void, a cosmic abyss, stands as a silent invitation to explore the universe's grandest mysteries. Its profound emptiness beckons us to venture beyond the familiar, to embrace the unknown. The void's silence whispers possibility, challenging our understanding and inspiring our imagination. It reminds us that the universe is more than the sum of its visible parts. Within its darkest corners lie secrets waiting to be uncovered. The Boötes Void stands as a beacon, a reminder of the universe's vast, complex mystery.
We often find ourselves racing through life, absorbed in our daily concerns, without a second thought about the true pace at which existence unfolds. But when we step back and look at the broader picture, beyond Earth, we begin to see the astonishing reality. We are speeding through the cosmic expanse, heading into regions where no photon or elementary particle has ventured before. Into the infinite void. Our solar system, our galaxy, and indeed the entire universe not only traverse space but actively expand, creating new space as they move. Feeling overwhelmed? Take a deep breath and join us as we embark on an extraordinary journey. We're setting out to explore the edge of the universe, and perhaps even a bit further. For our loyal followers, this isn't the first time we've ventured beyond the familiar bounds of our solar system and galaxy to ponder. What is the structure of the cosmos? What lies at the very edge of the universe? Does the universe have a center or limits? Is our existence part of a simulation, or is it reality? Could we be one of many worlds in a multiverse? With each discovery, scientists find themselves facing even more profound questions. Is the universe truly infinite, or just unfathomably large? Since its dimensions, age, and mass cannot be definitively measured, the notion of an infinite cosmos was born. According to Friedman's theory, a finite universe must be in a state of expansion or contraction. Yet, if the universe is infinite, the ideas of expansion and contraction become paradoxical. The concept that the universe could have emerged from a singularity the size of a neutron, as suggested by the Big Bang theory, challenges the perception of its infinity. If time is viewed as a linear vector moving forward with no reversal, it implies that time did not exist before the Big Bang. Einstein's theory indicates that space and time are interdependent, suggesting a moment when space might not have existed at all, or perhaps it did. Or maybe we simply do not know. The idea of an expanding universe began to take shape in the early 20th century when astronomers studied the behavior and distribution of galaxies. In 1912, American astronomer Vesto Melvin Slipher made a pivotal discovery that set the stage for future breakthroughs. He measured the redshifts of various galaxies and noticed that most exhibited Doppler shifts toward longer wavelengths, indicating their motion away from Earth. Building upon Slipher's work, Belgian astronomer Georges Lemaitre proposed in 1927 that the universe was expanding. But even before this, a significant breakthrough in mathematics occurred in 1915. It wasn't just the publication of Einstein's general theory of relativity, a groundbreaking work that revolutionized our understanding of gravity, space, and the dynamics of the universe, that made waves in scientific thought. What truly marked a pivotal moment in mathematics was the proof of a lesser-known yet fundamental theorem by Emmy Noether, Noether's theorem. This theorem was the first to show that in any physical system governed by conservative forces, where the action of the system displays differentiable symmetry, each independent differentiable symmetry corresponds to a conservation law. Simply put, when a physical system exhibits a certain symmetry, there is a physical quantity associated with that system that remains conserved. For example, if a system maintains rotational symmetry, meaning its behavior is unchanged regardless of its orientation, then angular momentum is conserved. This principle applies broadly, from spherical objects to celestial systems like the Moon orbiting Earth and the Earth-Moon system orbiting the Sun. These systems conserve angular momentum because the physical laws driving their motion remain consistent irrespective of their orientation, highlighting the theorem's importance. In 1929, discussions about the expanding universe gained momentum when Edwin Hubble published his findings. He measured the distances to galaxies and their velocities relative to Earth and discovered that nearly all galaxies are receding from us, with more distant ones moving away faster. This pivotal observation supported results derived from the general theory of relativity, as Alexander Friedmann and Georges Lemaitre had applied its equations to the cosmos and concluded that the universe under gravity could not be static. It must either expand or contract. The realization that the universe was expanding led to the formulation of the Big Bang theory, positing that all observed matter originated from a single, extremely dense and hot state. This expansion happened rapidly, yet it did not imply a specific center from which galaxies moved outward, leaving many mysteries to unravel. As previously mentioned, in the context of mathematics and symmetry, if a system exhibits symmetry with respect to spatial translations, linear momentum is conserved. What type of symmetry leads to energy conservation? This is known as time translation invariance. It means that the laws of physics governing the behavior of particles and fields remain unchanged when a system shifts forward or backward in time. This fundamental property underpins quantum laws that govern particles, quantum fields, and interactions, dictating particle-antiparticle creation and annihilation, and influencing gravitational experiments conducted on Earth, within the solar system, and across the Milky Way. As long as the laws of physics remain stable over time, energy conservation holds. This principle applies to the strong and weak nuclear forces, as well as electromagnetism. However, with gravity, this consistency only partially applies. The reason is that, unlike other physical forces that follow uniform rules regardless of time or place, gravitational interactions conserve energy only within a static, time-invariant spacetime structure, as described by Einstein's general theory of relativity. In scenarios involving a single-point mass, spacetime maintains its structure over time and follows an exact solution known as Schwarzschild space. In this context, the equations, coordinates, and laws remain time-invariant, ensuring energy conservation. However, in an expanding universe, this no longer holds true, complicating the notion of energy conservation for gravitational interactions. In our actual universe, the curvature of spacetime is shaped by the distribution of matter and energy. This curvature, in turn, governs the motion of matter and energy. The relationship is dynamic and reciprocal. The arrangement of matter and energy affects how spacetime evolves, and this evolving spacetime, in turn, influences the behavior and distribution of matter and energy within it. In a universe uniformly filled with matter and energy, as ours is on the largest cosmic scales, spacetime is not static like Schwarzschild spacetime. Instead, it is described by the Friedmann-Lemaitre-Robertson-Walker metric, named for the scientists who studied it. This type of spacetime must expand or contract over time. Static solutions are inherently unstable, similar to the fluctuating emotions of a teenager. According to prevailing theories, the universe began as an incredibly hot and dense singularity, marked by the Big Bang. In the first minuscule fraction of a second, the universe underwent rapid expansion, or inflation, growing at a pace that exceeded the speed of light. During this brief phase, the universe expanded by a factor of at least 90. Following this inflationary period, data from NASA shows that the universe continued to expand, but at a reduced rate. As space expanded, it cooled, enabling matter to form. Approximately 1 second after the Big Bang, the universe was filled with particles such as neutrons, protons, electrons, positrons, photons, and neutrinos. Around 380,000 years after the Big Bang, the cooling allowed atoms to form during the recombination era, resulting in a transparent, electrically neutral gas. This event marked the onset of a dark period in the universe, as stars and luminous objects had yet to emerge. About 400 million years later, the universe entered the reionization era, gradually transitioning out of the cosmic dark ages. Over 500 million years, gas clouds fragmented, forming the first stars and galaxies, whose intense ultraviolet light ionized most of the neutral hydrogen. Today, we know there is a clear relationship between a galaxy's distance and its speed of recession. For instance, a galaxy located 1 megaparsec away from Earth recedes at a speed of 70 kilometers per second. A galaxy twice that distance recedes at 140 kilometers per second. Presently, there are two main methods for determining the age of the universe, often represented by the Hubble constant. The discrepancy between these methods lies in whether they observe relatively nearby cosmic objects or those at extreme distances. Despite these approaches, scientists still obtain varying results, hinting at possible unknowns or unaccounted for phenomena in the universe. Although the expansion of the universe initially slowed due to the gravitational pull of matter clumping together, about 5 to 6 billion years after the Big Bang, an enigmatic force known as dark energy began accelerating this expansion, according to NASA. This acceleration persists today. One might wonder why the universe's behavior could not be simpler, but calculations indicate it cannot be otherwise. Will the universe contract? Modern physics and cosmology face two profound challenges. 85% of the universe's mass consists of unidentified matter, and most of its energy originates from an enigmatic source. Observations suggest that dark matter acts as the glue binding galaxies, while dark energy drives the universe's expansion. The presence of dark matter is essential. Without it, galaxies would not form, and life as we know it would not exist. However, the existence of dark energy poses a more unsettling implication. If it continues to dominate, the universe will expand indefinitely, potentially leading to a heat death. In this scenario, stars would burn out, no new stars would form as gas resources deplete, and the temperature of the universe would drop to levels incompatible with complex life. As spacetime continues to stretch, matter would become increasingly sparse, resulting in a universe expanding endlessly, devoid of observers or life. While this scenario might seem unsettling, it was once considered the most straightforward explanation in physics. However, the mysteries of dark matter and dark energy have proven so challenging that they now appear almost insurmountable. Attempts to attribute dark matter to unknown particles have so far come up short, and no widely accepted alternative has emerged. This situation is so difficult that some physicists have proposed revising gravitational laws to eliminate the need for dark matter entirely. Dark energy has presented similar difficulties. Initially believed to be a cosmological constant that exerted a uniform outward force across space, observations from the Planck Space Telescope told a different story. According to Planck, the universe's expansion rate inferred from cosmic microwave background variations, is 67.6 kilometers per second per megaparsec. In contrast, data from the Hubble Space Telescope, which observed nearby celestial objects, indicated an expansion rate of 74 kilometers per second per megaparsec. As Naked Science has reported, the dark matter problem is not entirely hopeless. Since the launch of the LIGO Observatory, an unexpectedly high number of mergers between stellar mass black holes have been detected. Such frequent mergers imply the presence of far more black holes than previously estimated. For years, researchers have searched for elusive dark matter particles, like WIMPs, only to conclude that they likely do not exist. Yet, discoveries made between 2016 and 2020 hinted that dark matter might not require a new particle after all. Instead, its nature could be different from what was once assumed. If so, our universe might be cyclical, a so-called phoenix universe that has experienced repeated cycles of expansion and contraction. Stellar mass black holes, formed from the remnants of stars, should be clustered rather than uniformly scattered across the cosmos, similar to how stars themselves are found in clusters. Dark matter, which accelerates the edges of galactic disks, is found in dark halos surrounding galaxies. This has led some scientists to theorize that black holes could form clusters within these halos. However, two major questions persist. What explains the sheer number of these black holes, and why does dark energy seem stronger in our galaxy's vicinity compared to regions billions of light-years away? A pivotal article by Gorkovy and Tielbashev, published in the Astrophysical Bulletin, advances the search for answers. The authors highlight that not all stars can become black holes. Only about 1 in 1,000, primarily the most massive stars, achieve this fate. Given the estimated 100 sextillion stars in the observable universe, only 100 quintillion would become black holes, a figure far lower than what would be needed to account for the black holes observed by LIGO as dark matter. This suggests an unexpected source is necessary. The researchers introduced the concept of a phoenix universe, in which our universe has already undergone numerous cycles of expansion and contraction, possibly more than hundreds. In each cycle, the universe begins by expanding, as it is now. It then slowly transitions into a phase of contraction. As contraction progresses, black holes move closer together. During the final stage, the universe's diameter shrinks from its current 100 billion light-years to just about 10 light-years. At such an extreme compression, the density and energy of the cosmic microwave background increase, raising the temperature from 3 Kelvin to an astonishing 10 billion Kelvin. At these temperatures, atoms composed of heavy elements break down under the bombardment of gamma photons, while black holes, immune to such destruction, remain intact. In this hyper-compressed state, only black holes and some neutron stars survive. The most intriguing aspect is what happens next. In this confined space of just a few light-years, trillions of black holes gather in close quarters, drastically increasing the frequency of mergers. Data from LIGO shows that each black hole merger converts about 5% of their combined mass into gravitational waves, which, as Einstein demonstrated, do not carry mass. Consequently, a considerable amount of mass in this contracting universe is converted into gravitational waves. With repeated mergers, the number of black holes halves, and the total mass of the universe decreases by at least 5% each cycle. This process continues, gradually reducing the universe's mass with each cycle and potentially leading to significant decreases over time. It's crucial to understand that the universe's contraction results directly from the gravitational pull of the matter within it. If significant mass loss occurs due to the merging of black holes, the gravitational mass may diminish to a point where it can no longer sustain contraction. Imagine reducing the sun's mass gradually within the solar system. Eventually, it would become too light and the planets would drift away. While not a perfect analogy, since the universe lacks centrifugal force, the principle highlights an essential concept of gravitational balance. In the Phoenix universe model by Gorkovy and Tielbashev, as the universe compresses to around 10 light-years in diameter, heavy atomic nuclei are destroyed by gamma photons, while black hole mergers convert much of the dark matter into massless gravitational waves. When this transformation reaches a certain threshold, the contraction halts, triggering rapid expansion, the new Big Bang, marking the start of another cosmic cycle. At this stage, heavy elements no longer exist. Over time, as the universe expands and cools, the temperature drops enough for atoms of light baryonic matter, such as hydrogen and helium, to form. The supermassive black holes that survived the prior cycle serve as gravitational centers around which these gases coalesce, eventually forming galaxies. Gorkovi and Tyolbashev refer to these as seed black holes, foundational to galaxy creation. The concept of galaxies forming around central massive black holes isn't new, supported by observations of ancient early universe objects, but their mechanism had been unclear until now. The theory suggests that the Big Bang results from some dark matter, black holes, turning into gravitational waves. Yet the significance of these waves extends beyond their creation. When gravitational waves interact with black holes, they are absorbed, increasing the mass of black holes, essentially the dark matter in our universe. As this mass grows, the expansion of space slows, eventually reversing into contraction. The process resembles a massive pendulum. Kinetic energy shifts to potential energy as the pendulum climbs until it peaks, slows, and descends. Similarly, as the universe expands, gravitational waves' energy is converted into mass, leading to eventual contraction. At the contraction's peak, black hole mergers release energy as gravitational waves, igniting another explosive expansion, the next Big Bang. Superstring theory, once popular, lost traction when it failed to produce verifiable predictions. Gorkovi and Tyolbashev argue that supporting evidence for their model already exists. Their calculations align with the number of stellar mass black holes needed to explain LIGO's observed merger rates. Although frequent mergers occur, the number of black holes grows with each cycle, suggesting they could be far more plentiful than in a single-cycle universe. The abundance of black holes aligns with a universe that has undergone repeated cycles, making sense of the impossibility of deriving 100 sextillion black holes from 100 sextillion stars alone. Moreover, their model's estimate of supermassive black holes from previous cycles corresponds to current observations, where there is approximately one supermassive black hole per large galaxy, around 100 billion in total. Earlier cosmological models struggled to explain the existence of billions of such massive black holes so early in the universe's history, but this cyclical model provides an explanation. Yet, matching existing data isn't enough. A robust model must make new, testable predictions. The study's authors suggest that searching for dark globular clusters of stellar mass black holes in galaxy halos could be such a prediction. They conclude that analyzing stellar movements in astrometric catalogs, such as Gaia data, might reveal these hidden clusters within the galaxy disk. The rationale here is straightforward. As dark globular clusters pass between Earth and a star in another galaxy, they may occasionally create a gravitational lensing effect. This occurrence, while rare, would stand out distinctly against the backdrop of the sky, making it easier to identify. A standout feature of this model is its prediction of an extraordinarily massive black hole somewhere in the universe, far surpassing any supermassive black holes discovered to date. This colossal black hole would be so vast that eventually it would absorb the entire universe, including Earth and all its inhabitants. However, this concept does not imply a doomsday scenario in the traditional sense. Falling into a black hole only results in spaghettification, a violent stretching and death, if the black hole is of relatively small stellar mass. In contrast, entering a supermassive black hole would not produce such an effect. Due to its immense size, the tidal forces acting on different parts of a body would be minimal, avoiding the spaghettification effect. Falling into such a massive black hole would likely be painless and might even go unnoticed by most, except for astronomers. They would observe the gradual fading of the redshift from distant galaxies, signaling the approach of the main black hole's boundary. Eventually, this redshift would shift to blue, indicating the universe's contraction as the expansion halts and reverses. While this process may span billions of years, it doesn't mean Earth's civilization would survive. The contraction of the universe, according to Gorkovi's calculations, may take another 10 to 20 billion years until expansion ceases, with the contraction phase lasting an additional 20 to 39 billion years. The end is inevitable. Initially, the night sky would become intensely hot, making life on all planetary surfaces unsustainable. Eventually, as the universe continues to shrink, temperatures could soar to 100 billion degrees, and gamma rays from relic radiation would obliterate all atoms. Survival through this contraction phase of the Phoenix universe seems unlikely. Whether there is any escape remains unknown. This groundbreaking article suggests a bold shift in cosmology, proposing one of the first comprehensive and logical explanations of dark matter and dark energy. According to this theory, dark matter is composed of relic black holes, while dark energy does not actually exist. The supposed repelling force of dark energy is instead attributed to the influence of the main black hole. This concept also explains why the universe's expansion rate is slower at distant points compared to the nearby universe. If the universe's expansion is a consequence of mass loss over time, the rate would indeed differ between the distant past and the present. The concept of dark energy demands a consistent expansion rate, but in this new model, the absence of dark energy nullifies this need. Another strong point of this theory is its explanation of a fundamental mystery in galaxy formation. For a long time, scientists have noted that galaxies could not have formed without the presence of supermassive black holes at their cores. Observations reveal these massive black holes already existing within the universe's first few 100 million years, some weighing billions of solar masses. This new model naturally explains their origin. Like the stellar mass black holes that form dark matter, they were inherited from previous universes that preceded our own Big Bang. This also implies that the earliest universe likely lacked a significant number of galaxies, as it did not yet have the seeds, massive black holes, to pull gas together and form galaxies. Transitioning from the strengths of the new theory, we must also consider its potential weaknesses. It is unlikely, to put it gently, that the work by Gorkovy and Tyulbashev will be rapidly or widely embraced by the scientific community. The theory deviates too significantly from the established one-time universe model. While the notion of the universe undergoing numerous cycles of expansion and contraction isn't entirely new, even George Gamow, who predicted cosmic background radiation, entertained such a concept. The mechanisms introduced by Gorkovy and Tyulbashev are distinctly unconventional. They propose that the universe contracts as black holes gain mass and expands when black holes release mass through gravitational waves. This marks an unprecedented shift in cosmology, so novel that it falls outside the consideration of most physicists. Critics of the theory may find it so unfamiliar that they overlook Einstein's well-documented assertion that gravitational waves possess no mass. Detractors claim that the total mass in the universe cannot diminish, arguing that when black holes emit gravitational waves, this mass merely transitions, not diminishes, from one form to another. Another potential challenge is that accepting this model could lead to the abandonment of entire areas of research, including the hunt for WIMPs, dark energy, and certain quantum gravity theories. Historically, proponents of mainstream scientific paradigms have been reluctant to acknowledge when their theories become outdated, so it's improbable that this theory will be received differently. Dark matter and dark energy are currently focal points in modern astrophysics. The mystery surrounding dark matter has been recognized for quite some time. In 1884, Lord Kelvin noted that stars in the outer regions of the Milky Way's disk were orbiting the galactic center at far greater speeds than theoretical calculations suggested. To reconcile this discrepancy, it was necessary to hypothesize the existence of vast unseen mass beyond the visible disk, in the dark outskirts of the galaxy where no stars are present. Although Kelvin did not name this phenomenon, it was the French mathematician Henri Poincaré who in 1906 described Kelvin's observations and coined the term dark matter. Despite more than a century of investigation, our understanding of dark matter has seen limited progress. While we have gathered extensive data on other galaxies, these observations consistently reveal the same pattern. Massive, invisible forces influence the motion of stars on the outskirts. The term enormous is appropriate, as current estimates suggest dark matter constitutes about 26.5% of the universe's total mass, compared to just 5% for ordinary matter, the material that makes up stars, planets, and all known life. Yet, the precise nature of this vast unseen matter remains a mystery. Up until the mid-2010s, weakly interacting massive particles were the leading hypothesis for explaining dark matter. This theory suggested that dark matter particles interact minimally with regular matter, primarily through gravitational forces. However, various analyses, including those by Russian scientists, indicated that even if WIMPs exhibited weak non-gravitational interactions, their abundance would be such that they would pass through a human body at least once a day, potentially much more frequently. Theoretically, under certain conditions, WIMPs could damage human cellular DNA and potentially lead to cancer. Fortunately, extensive experiments conducted on Earth have found no trace of WIMPs. Physicists now agree that no known particle possesses a cross-section small enough to align with such behavior. Astrophysicist Ethan Siegel elaborates on the issue, stating that even if particles with these properties could exist, there would not be enough of them to account for the entirety of dark matter. Despite these setbacks, proponents of the WIMP theory remain persistent. Siegel wryly remarks, "Theorists can always adjust their models, and they've done this time and again, lowering the expected WIMP cross-section after every experimental null result. This is the poorest form of science. The only motivation here is to uphold an idea that actual data dismisses." Although research into WIMPs continues globally, using costly detectors, it now resembles a futile search, like someone hunting for lost keys under a street lamp, simply because it's the only spot with light. The most likely result of ongoing WIMP research is further years of inconclusive experiments, with no discoveries. Hopefully, however, some valuable insights will emerge during this pursuit. This brings us to a fundamental question. If WIMPs don't exist, could dark matter be composed of other types of particles that might be equally or even more dangerous? Or could it be something entirely different? Enter the MACO theory. MACO stands for Massive Compact Halo Object. In a galaxy, the halo is a spherical cloud of matter extending far beyond the visible disk, encompassing areas above and below it as well. Unlike WIMPs, MACOs aren't theoretical particles, but instead represent dense, dark objects. The main candidates in this category are black holes and neutron stars. Until recently, there were three key reasons why MACOs were not considered sufficient to explain most dark matter. The first reason involved the frequency of gravitational lensing observed in astronomical studies. Black holes, being highly dense and massive, create a gravitational lens effect when they pass between Earth-based telescopes and distant stars, amplifying the star's light significantly before gradually fading as the black hole moves out of alignment. Observations show that the actual frequency of such lensing events limits the number of MACOs present, suggesting that they cannot account for all the dark matter. The second reason concerns the amount of ordinary baryonic matter produced during the Big Bang. Both black holes and neutron stars are formed from baryonic matter, and calculations indicate that if the Big Bang had created enough of it to account for a third of the observable mass of the universe, the isotopic ratios observed in stars would be markedly different from what we currently see. Thirdly, black holes and neutron stars are the remnants of massive stars at the end of their life cycles. The challenge lies in the fact that stars massive enough to evolve into neutron stars or black holes are exceptionally rare, representing less than 1% of all stars. Estimates suggest that only 1 in 1,000 stars will ultimately collapse into a black hole. This poses a significant problem. Dark matter is estimated to be 5.3 times more prevalent than the visible matter in the universe. How could this be possible if MACOs originate from such a tiny proportion of all luminous stars? Quite simply, there aren't enough suitable candidates to produce MACOs in the quantities needed to account for the vast amounts of dark matter observed. Up until 2016, the prevailing belief among astronomers was that while MACOs existed, their contribution to the total mass of dark matter was minimal. This assumption was bolstered by the expectation that WIMPs would eventually be detected. a discovery that, to this day, has not occurred. The situation took a dramatic turn in 2016, thanks to the groundbreaking observations by the American LIGO gravitational wave detector. Over several years of intermittent operation, LIGO detected dozens of gravitational wave signals with varying levels of statistical significance, including more than a dozen confirmed with high reliability. Most of these signals were the result of black hole mergers or collisions between black holes and neutron stars. The detected black holes had masses ranging from several solar masses to dozens. This discovery raised a significant question. How could there be so many black hole mergers, especially involving black holes with such unusual masses? Before LIGO's operations, black holes of tens of solar masses were thought to be extremely rare. This dilemma is compounded by the fact that astronomers have developed methods to observe mergers of ordinary stars, where material from one star transfers to another before culminating in an explosive outburst. These events are not common, and black hole mergers were expected to be even less frequent. Given that only 1 in 1,000 stars evolves into a black hole, and that a merger requires a black hole to find a suitable companion, the odds seemed astronomical. Black holes have an average diameter of roughly 100 kilometers, so how could they draw close enough in the vastness of space to merge? Moreover, the formation of a black hole follows a supernova explosion, a powerful event that typically propels the black hole out of its original stellar system at high speed. This makes it even more improbable that two black holes, each expelled from different supernovae, would encounter and merge in the vast expanse of interstellar space. How could such rare events occur frequently enough for LIGO to register multiple detections each year? Since 2016, some researchers have proposed that the black holes detected by LIGO might actually be MACOs. This theory suggests that a new category of extremely dark compact objects could be the key to solving the dark matter mystery. However, two major challenges remain: the previously noted scarcity of observed gravitational lensing events and uncertainty regarding how such a vast number of black holes could have formed in the universe. In 2017, an unconventional idea emerged. MACOs may not need to be uniformly distributed throughout the galactic periphery. The stars believed to give rise to these black holes often form globular clusters at the edges of galaxies. These clusters are dense formations, containing anywhere from tens of thousands to 1 million stars, packed at distances averaging half a light year apart. In these regions, the night sky would be 100 times brighter than in our solar neighborhood. If black holes were to form similar dense, dark globular clusters, comprising a few thousand black holes each, the number of detectable gravitational lensing events would remain low. While each cluster could act as a significant gravitational lens, the chances of one aligning between Earth and a distant star would be minimal. The concept of dark globular clusters is particularly compelling because it could also explain the frequent black hole mergers detected by LIGO. The odds of two black holes approaching each other by chance are low, but within dense dark clusters, eventual collisions become far more likely. By 2019, another research team found that the mass of a galaxy's halo, estimated from the gravitational effect of dark matter, correlated closely with the number of visible globular clusters. Multiplying the number of these clusters by approximately 5 billion solar masses yielded a figure close to the total estimated mass of dark matter in a galaxy's halo. How do dark globular clusters fit into this? The answer is straightforward. Visible globular clusters typically do not exceed 1 million solar masses. However, there should be a significant relationship between the number of visible star clusters and unseen clusters of black holes and neutron stars. If these dark clusters form the majority of dark matter, they would exert the gravitational influence necessary to bind the visible clusters to their galaxy. This hypothesis is promising because it explains dark matter without introducing new particles. It is also verifiable with current astronomical techniques. Dark clusters would cause localized star disturbances at the edges of galactic disks as they pass by, leaving observable trails. This concept suggests that clusters of black holes and neutron stars could provide a more convincing explanation for dark matter than WIMPs or other theories involving unknown, elusive particles. Yet, one major issue remains. In a study by gravitational physicist N. Gorkovy and similar research, estimates indicate that up to 200 billion black holes with masses of around 5 solar masses would be required in our Milky Way alone. Given that the Milky Way holds approximately 400 billion stars and only a fraction could evolve into black holes, this hypothesis would necessitate several hundred billion black holes, far more than expected from known stellar processes. The mysteries of our universe extend far beyond just our own galaxy. According to current Big Bang theories, there's no clear indication of how such a massive amount of ordinary matter could have accumulated to form so many stars, which would ultimately give rise to an enormous number of black holes. Where could they have come from? We've been grappling with this question too. Interestingly, we still don't know if ours is the first universe, or if space-time undergoes cycles of expansion, like what we see now, followed by contractions and new beginnings. Observations today don't definitively distinguish between these possibilities. What does all of this suggest? The question of whether machos might ultimately prove superior to WIMPs and other dark matter candidates could be answered in the next decade. The Gaia Space Telescope is well equipped to detect perturbations caused by dark globular clusters within fields of bright stars. But it's important to note, even if machos do emerge as the solution, this may not offer as much comfort as we'd hope. While it could explain the dark matter puzzle that's puzzled scientists since 1884, the implications are profound. Today, the Standard Model places the age of the universe at about 13.8 billion years. Its story seems straightforward, a progression from an unfathomable initial density at the Big Bang to today's intense expansion in all directions, creating a roughly spherical universe with a span up to 100 billion light-years. But if black holes indeed account for dark matter, this simple linear narrative becomes far more mysterious. It would imply that our space-time may have cycled through countless eras of expansion and contraction, meaning that any solitary black hole or neutron star beyond galactic disks could be trillions of years old, predating even the formation of atoms. This Phoenix universe scenario is far more complex and vast than anything modern cosmology has depicted so far. In trying to address challenging questions, machos might only present physicists with even greater ones, questions that could prove exceedingly hard to answer definitively. In the massive survey, researchers at the University of California analyzed nearby massive galaxies within 100 megaparsecs of Earth, and in doing so, they inadvertently measured the Hubble constant, or the rate of the universe's expansion. Their findings differed from earlier models, showing a speed roughly 9% higher than theoretical predictions. This figure aligned with results published 2 years prior by Johns Hopkins University. Guided by Professor Ma-Chun Pei, the California team examined 63 elliptical galaxies using both ground-based and space telescopes, measuring variations in brightness to calculate both the galaxies' distances and their recession velocities. Nobel laureate Adam Riess's team at Berkeley, which famously demonstrated in 2011 that the universe's expansion is accelerating, had observed a similar discrepancy while studying stars in the neighboring Large Magellanic Cloud with the Hubble Space Telescope. They too found a speed about 9% higher than theoretical models suggested. Their findings, published in astrophysical journal letters, brought further attention to the mystery. We've long known the universe is expanding, but why it's expanding faster than anticipated remains unknown. While calculations point to one rate, observations reveal a quicker pace. Conventional wisdom says that for every megaparsec of distance from Earth, a galaxy's recession speed should increase by 67 kilometers per second. Yet Rice's measurements show an increase of 73 kilometers per second, a difference of 9%. Observations hinting at accelerated expansion date back to 2016 and were reaffirmed in 2018 with data from the European Space Telescope, Gaia. Now, Berkeley's latest findings have further strengthened this conclusion. with two independent groups arriving at near-identical results. Ma-Chun Pei and her colleagues detailed their findings in the Astrophysical Journal, attributing the accelerating pace of galactic movement to either dark matter or dark energy. Although these phenomena are not well understood, scientists believe that the repulsive forces they exert far outweigh gravitational pull. Robert Caldwell of Dartmouth College, along with researchers from the California Institute of Technology, explored one possible fate of this spreading apart phenomenon. They proposed that the universe could eventually reach a big rip, where it would expand so extensively that all matter, down to its smallest components, would be torn apart. Fortunately, this catastrophic event is predicted to be far in the future, about 22 billion years from now. But given the current pace of acceleration, this end may be drawing closer, accelerating, in a cosmic twist of fate. If the Big Rip scenario unfolds, the sequence would be catastrophic. 60 million years before the final breakdown, the Milky Way would be torn apart. 3 months before the end, the planets of our solar system would scatter. In the last half hour, Earth would crumble to dust, and ultimately, even atomic nuclei would disintegrate, leaving no trace of matter as we know it. What might come after the Big Rip? Perhaps absolute nothingness. But there's a chance that dispersed matter could coalesce into an unimaginably dense point, a singularity, which might trigger a new Big Bang. Much like the one that created our universe 14 billion years ago, this event could lead to the birth of a new universe. In contrast, scientists working on the Gamma Project, who study radiation from stars and star clusters across different wavelengths, have projected a longer life for our universe. Surveying 220,000 galaxies, they found that these galaxies' radiation is gradually dimming. In 2015, Professor Simon Driver from the International Center for Radio Astronomy remarked that the universe is slowly darkening. This fading, they concluded, will eventually lead to a universe void of light, like a lamp running out of fuel. If we trust the Gamma team's research, the universe may not be eternal, but complete darkness is still a distant event. Based on current calculations, all stars will burn out in 100 trillion years. After another 1,016 years, any remaining star material will be consumed by black holes. Eventually, in about 1,099 years, even black holes will disappear. This, in cosmic terms, is as close to eternity as we can imagine.